prime numbers versus smooth numbers. So what I want to do is talk about some kind of classical multiplicative number theory problems that are studied for the primes and the analogous questions for smooth numbers, and see what the similarities and differences are between the two cases. And sometimes the smooth numbers are easier to study and we can say more, and sometimes the contrary. And I'll try to explain why that is. So I'll start by telling you what a smooth number is. So definition. A number n is said to be y smooth. If whenever a prime p divides n, p is less than y. So kind of informally, a smooth number is one that only has small prime divisors. We'll be thinking about all the smooth numbers up to some size x, where y has some size compared with x. So maybe y is square root x, or y is e to the root log x, or y is log x to the power of 1,000,000, something. And there's a traditional piece of notation which I'll just write down at the start. So it's traditional to write u is log x divided by log y, because this comes up all over the place. Okay. So traditional to write u is log x over log y, and kind of one of the goals here is to get results that apply as uniformly. So x is how far we're going to count. So say n is less than x. Yeah, and we want to get results that hold as uniformly in y as possible, as long as wide a range of y relative to x as possible. Okay, so what kind of questions do I want to talk about? So firstly, maybe I just want to count how many y smooth numbers there are less than x. And in the prime case, this is the question that's sort of answered by the prime number theorem. And then once I can do that, I might want to count the y smooth numbers less than x that are congruent to A mod q. And in the prime case, this is the prime number theorem in arithmetic progressions, or the Siegel-Wolfert's theorem if I want some uniformity in Q relative to the size of x. And in the prime number case, the kind of uniformity that we can get is a bit bad because of the possible malign influence of the Siegel zero. And it turns out that in the smooth number case, that's very different. So that's one of the things that I want to kind of point out. And then once we can do this, I want to talk about counting in APs on average over Q. And in the prime case, this is the Bombieri Vinogradov theorem. And so the new result, which I'll get to towards the end of the talk, is a Bombieri Vinogradov type result for smooth numbers. So I'm just going to go through these things in order, but before I do that, I want to flag up some things that you should look out for that will come out in the course of the talk. So one is saddle point. Saddle point argument of Hildebrand and Tenenbaum. So this is something that they developed to count y smooth numbers, and it's also very important to all the kind of recent analytic work on the other problems that I wrote down. So the next thing is status of Siegel zeros. So in the prime case, if there is a Siegel zero, which is unlikely but we can't rule out, this will distort the distribution of primes in arithmetic progressions. Okay, but in the smooth case, Siegel zeros do not have this effect. So this makes a difference, for example, to whether we can make the results effective or not in terms of the constants. And the other thing is sparsity of smooth numbers. So there are actually quite a lot of primes around. There are about x over log x primes less than x. Whereas if y is kind of small, there aren't really a lot of smooth numbers around. They're a much sparser set. And typically in analytic number theory type problems, if your set is sparser, that makes it harder to study. And we'll see that when I get to the Bombieri Vinogradov result at the end. Right. So
which is then by completely different methods.
Right. So certain kind of additive questions and small gap questions with smooth numbers can be studied differently and more successfully than in the prime case, at least when y is large. So when y is x to the epsilon or something like this.
I don't have anything new on that.
No. Right. So start talking about counting smooth numbers or primes. They are less than x. Okay, so what do we do in the prime case? Well, we look at the Dirichlet series corresponding to the primes, more or less. And this can be expressed in terms of a nice Dirichlet series, the zeta function. And then, given this, we can express the counting function that we want as a contour integral, more or less. Okay. And then what I just want to point out about this is, so what do we do now? Where does the main term come from? So if we want to count the primes, we want an asymptotic formula with a main term and an error term, which is lower order. Where does the main term come from? It comes because we shift the line of integration and we encounter a pole of this guy. So we get a residue there, and then we can shift a little bit further without encountering any more poles, any zeros of zeta, and we get a lower order error term. So that's all I want to say about that, because that's in contrast to the smooth situation. Okay, so in the smooth case, what's the Dirichlet series that corresponds to smooth numbers? It's just this guy. Restrict to numbers that only have prime divisors more than y. Now I can write this as finite Euler product. And this now converges, and this now converges absolutely whenever the real part of S is strictly larger than 0, because there are only finitely many terms in the product. Okay, but now you can still try to do the same thing as up there. So number of n less than x, n is y smooth. This is written psi xy traditionally. And this is more or less like so we'll call this zeta s y. Right. So we have the thing we want expressed as a contour integral. But now, if we were kind of modeling what was happening up there, we want to try and get a main term by finding a pole of zeta sy and finding a residue. But we're not going to be able to do that because there aren't any poles, at least in the half plane that we're interested in. So as I said here, this thing converges absolutely wherever the real part of S is strictly larger than 0. So when we shift past 1, there is no pole. So where is the main term going to come from? And this thing, which maybe seems like a trivial problem, this held up the analytic study of psi xy for a long time. And this is the thing that was resolved by Hildebrand Tenenbaum. Okay, so what they said is we're going to shift the line of integration to a specially chosen place. So shift to the line, real part of S is alpha of xy. And what is alpha of xy? So it's argmin of that thing. It's the real value of sigma strictly larger than 0 that minimizes x to the sigma, zeta, sigma y, where zeta, sigma y is the partial order product up there. Okay, so as sigma tends to 0, this diverges to infinity. As sigma tends to infinity, this is going to infinity. So somewhere in between there, there's some minimum value. And it turns out that, so this is a product over primes. So we can get some information about what this value alpha is. And at least if y is like that, say, where u is log x divided by log y, as I said before. So when y is very close to x, this is small, this is big, so the point alpha is close to 1. And when y gets smaller, then u gets bigger, y gets smaller, so this is moving closer to 0. And what's the point of this? Well, they showed that psi xy is x to the alpha zeta the value of sigma which minimizes the expression in the brackets. Minimizing the argument which minimizes the expression. So alpha is the value of sigma which minimizes this expression. Yes. Yes. Yeah. I don't want the minimum of this expression. I want the value of sigma which minimizes this expression. Okay. 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 So they showed this uniform expression for psi xy as long as u tends to infinity and y tends to infinity. And if those things don't occur, then it's much easier to analyze anyway, because either y is close to x logarithmically or y is very small, and you can use geometric methods. And this expression here is maybe not so explicit as you would like to see, but it is very useful for analytic things, as we will see. And just to give an idea, so it turns out that all this other stuff is kind of lower order corrections, and it's just the x to the alpha that's mostly describing what's going on. So roughly, so very roughly, this is like x to the alpha, which is like, from here, x to the minus log okay, log x over log y is u.
You see the Dickman function and the differential equation?
For what? The differential equation for what?
Dickman, suppose take y x to the epsilon.
Yes.
Asymptotics is a well-known function.
Yes. So you can recover. So I think in this way you can get new information about how the Dickman function behaves, but I don't think you can directly obtain the Dickman function from this expression. So you know the two things are equivalent on a wide range, so therefore you have some more information about the more classical expression. Right, so for example, if u is square root log x, which is when, okay, so y is e to the root log x, that's u is root log x, then this guy here is pretty small. This is like e to the minus root log x. So this is much, much sparser than the primes, which have density like 1 over log x, as I said at the start. So this is something to bear in mind when we get to the Bombieri Vinogradov result at the end. And maybe I should say the reason why this works, the reason why it's a good idea to put the contour at that place, is because then most of the contribution to the contour integral comes from a very little kind of box very close to the real axis. And there the derivative of this function is 0, so you can understand using Taylor expansions what's going on. And as you move further up and down the contour, the contribution is of smaller order. Okay, good. So we did the first thing I said. We counted smooth numbers. So now we want to do arithmetic progressions. So count smooth numbers or primes that are congruent to A mod Q. And let's say that the highest common factor of A and Q is 1. So how are we going to do this? Well, just so introduce Dirichlet characters. To detect the congruence condition. So Okay, so this is a standard thing. And then for the sum in the middle here, we again have a contour integral expression. So this is kind of like okay, and what's going to go on here? So we expect that the main contribution ought to come from the principal character, the one that's essentially 1 everywhere. And this one we analyze the same as we did zeta before. And from all the non-principal characters, we expect to get a smaller order contribution. And this is encoded by, there is no pole of this function at 1 when the character is non-principal. So we shift without encountering a main term, and we get something that's lower order, hopefully. But there's an issue here because for all we know, so maybe there is a real 0 of ls chi very close to 1. That is an exceptional 0, it's equals 0. And if there is, then the supposedly lower order contribution from that L function will be not very much lower order. And this is why you have this restriction that q is at most some power of log x in the Siegel-Wolfitz theorem. That's why you can't take q bigger. Okay. Right, so how about in the smooth numbers case? Well, analogously to there, you can introduce some L functions, ls chi y. Okay, and analogously to there, you would expect that if chi is not the principal character, then you get a smaller order contribution from the corresponding L function. But let's think about what happens if there happens to be a Siegel 0. So this thing is roughly like exp okay, just by taking logs and Taylor expanding. Now my claim is that if there is a Siegel 0, okay, a 0 really close to 1, within distance 1 over log q of 1, or 1 over 1 million log q, say. Right. If there is a 0 like that of ls chi, then chi of b is like minus 1. Most of the time. So the fashionable way to say this is that chi pretends to be the Mobius function. Chi looks like minus 1 on most primes. So I won't properly explain this, but I guess you can roughly think that ls chi is like the same thing here, but with the sum over all p. And if ls chi is being 0, then this thing needs to be pretty large and negative. That's kind of informally the situation. Or if you think about the explicit formula, the contribution from the zeros comes from the minus sign. So if you have a real 0 very close to 1 in the explicit formula, it's giving a negative contribution. Right. So this is true, and therefore, so if there is a c equals 0, so I guess I haven't said, I'll say that in just a moment. So the point will be that it's not the c equals 0 that determines that. It's determined by other things. Right, so if there is a c equals 0, this, meaning that, is large but negative when s is real. So if it's large but negative, and we take the exponential of it, we get something small. So even if there is a c equals 0, ls chi y is not big, like in the prime case, but it's small. So this is why c equals 0s don't cause a big disaster for the distribution of smooth numbers in arithmetic progressions, because everything's going on in this exponent here, and if the sign is right, which it is, then you still get a small order contribution. So if we take a mum, work this out in, I think, 1991, and they got equidistribution theorem for smooth numbers in arithmetic progressions as long as y is more than e to the c log x squared, and as long as q is smaller than, I think, e to the root log y, more or less. So this is much, much better than in the Siegel-Wolfitz theorem for primes, at least if y is moderately large. And that's because there's no malign influence from a c equals 0. And this is being improved now, so it's basically improved by Soundarajan, and I tweaked it a little bit, so you can have y to the 4 root e minus delta here. So you can go all the way up to a power of y. And the 4 root e there, that might be very familiar to some people, and it is not a coincidence. Okay. For any arbitrary fixed delta. And in fact, you can probably get rid of it altogether because there are these continuity results for sums of multiplicative functions. Right, so now I finally want to get on to the Bombieri Vinogradov theorem, which is what all this other stuff has been preparation for. So what I want to do is to give a bound. Let's start with the primes case. So give a bound for bound for that beats trivial bound. Which I will tell you is x log x. When q is, roughly speaking, square root x in size. So we would like to do it when q is bigger than square root x, but we can't at the moment. But we can do this. So, okay, and this is the expected size of this guy if we have equidistribution of primes in arithmetic progressions. So if we do have that, which we think we do, then we should get some cancellation in these sums and beat the trivial bound. Right. So how do you do this? Okay, well, first of all, the same as for individual progressions, switch to Dirichlet characters. Okay. Switch to Dirichlet characters. So you end up wanting to bound something like okay, the principal character is the main term which we've subtracted away, so we have this. And then, so if chi has small conductor, then you can use the Siegel-Wolfitz theorem. The result about primes in progressions to small moduli, which was proved by bounding character sums like this. So then what are we going to do with characters of large conductor? And they get quite large, they get up to square root x, maybe. And there are kind of two approaches to this. Okay, so the first one is the one that's often presented in kind of modern treatments of the Bombieri Vinogradov theorem, and that is that, so I can try to decompose this guy, roughly speaking, as a double sum. For certain coefficients am and bn, so that the sums aren't trivial. So there's some stuff here and there's some stuff there. And I can do this, for example, using the identity of Vaughan. And then I use Cauchy-Schwarz. So I want to bound sort of an L2 norm. Of character sums. And I want to do this on average over the characters and the moduli, but maybe with some slightly crazy coefficients am and bn inside. And fortunately, there's a great tool to do this, which is the large sieve. So I will write down a statement of the large sieving inequality in a moment, because that will be relevant. Okay, but this is one approach. So you break into these parts so you can Cauchy-Schwarz efficiently, and then you can use the large sieving inequality directly. Right, so that's one, but this is not how the theorem was proved originally. So the other option is sum over n less than x, lambda n chi of n. This is a contour integral, as we saw before. Or maybe you'd be better off using the explicit formula here, so you get out the contribution from the zeros more explicitly. And then you can use zero density results. To say So that's all very kind of vague, but there are these results called zero density results, which are proved using the large sieve. And they say that, okay, so for every LS chi, we expect that the non-trivial zeros lie on the critical line. Can't prove that, but there are these results which say that for most of them, there aren't many zeros very far away from the critical line. And that means that for most LS chi, you can shift the contour here much further than you know unconditionally for any individual one. You can get a much bigger saving. And when you add them all up, that's enough to get the theorem out. So now I will write down a zero density result, because since that's in the title of the talk, I think you should see one. And I'll write down the large sieve inequality, and then I'll talk about the results for smooth numbers. Okay, so this is just kind of for information. What does a zero density result look like? So it says something like, if I sum over all q, some range, and sum over all primitive characters mod q, okay, so just to explain, I count over all moduli q on some dyadic range, over all primitive characters modulo q, and I count all the zeros of all those L functions that have real part bigger than some sigma and imaginary part less than some t. And I get a bound for the number of zeros that there are. The trivial bound here is roughly like q squared t. Have about q squared things here and about t zeros up to that height. And this is saying that if sigma is very close to 1, if I'm only counting things that are sort of towards the edge of the critical strip, there are many fewer zeros than that. Okay, so this is, if you haven't seen a zero density result before, this is one. And I want to write down large sieve inequality as well. Okay. Yes, so what I stated, right, so what I stated is correct, I believe, because of a log-free zero density estimate.
What's the explanatory?
3, yes. So usually, so, right, so, right, so, So
So to remove the log, you have to work with an
I agree. So nevertheless, I think what I wrote there is correct. So
I'll give a proof in my little book.
okay, so to clarify all that, so the usual way to state the zero density result has some kind of exponent there, and it has a log factor at the front here. And that's unimportant when you're some macroscopic distance away from 1. When you're very close to 1, this log factor might even make the result trivial. But you can get rid of it, but that's much harder. So that's the log-free zero density result of Linnek, Gallagher, and other people.
But if you have improved zero-free regions, then you don't care about these log factors anymore.
That's true, but we don't have this for generic L functions. Okay. And I wrote this for a reason. Having the log-free thing is important for what I'm going to say. Okay, so this is a large sieving inequality. Roughly what it says is, how big can the left side be? Maybe there's one really big value of one of these sums, and that's more or less what this guy corresponds to. This has size like n times this sum, and there's a 1 over 5q. Or maybe all of them have about square root cancellation, and that's what the q corresponds to. So if you haven't seen that before, you can just believe me or ponder it as the boards switch over. Yes. I need to use the mess I had before to prove the result though. Right, so let me try and explain what this result says. So psi xy qa, this is the number of y-smooth numbers less than x to the congruent to a mod q. Psi q xy, this is y-smooth n and q are coprime. The number of y-smooth numbers less than x to the coprime to q. So unlike in the primes case, it isn't the truth that y-smooth numbers are only supported on co-prime residue classes, but on the co-prime residue classes you expect to have equidistribution. So this is the natural main term. And we're summing over Q, and then we get a bound. And the trivial kind of bound for the left-hand side is psi xy log x, analogously to, in the prime case, it was x log x. And so we get some kind of saving over the trivial bound. And again, we get some kind of saving as long as Q is a bit smaller than square root psi xy. And that's the analog of being a bit smaller than square root x in the primes case. Okay, so this is the result that I proved, and this was known. For y larger than x log to the 2/3 plus epsilon x, and that's due to Fufley and Tenenbaum again. Okay, so what I'll just try to explain in words is why they have this restriction and how I got rid of it. So if you look at the large sieving inequality, which is unfortunately covered up, right, so I kind of vaguely said before that the two terms here correspond to the typical behavior if you had square root cancellation everywhere and if there was one really big value. But that's only true if the sequence AN is fairly densely supported on all the numbers. If AN is sparse, then what's the biggest this could be? It could be like the support over Q times this guy, and that might be much smaller than N over Q. Maybe I should have something much smaller than N here. We don't know how to do that. We don't, in general, have large sieve results that can take account of the sparsity of the set. And as I said at the start, the y-smooth numbers, they get very sparse when y is small. And this restriction here exactly reflects that. So once y gets smaller than this, they're too sparse, and the estimates that come from a large sieve, they're not sufficient to get the result. So instead, how does the proof kind of go? The first part, handle characters. Of small conductor as for individual arithmetic progressions. So the same as in the classical Bombieri Vinogradov theorem with the prime to use the Siegel-Wolfitz theorem. And I won't say exactly what small conductor means. And then I'm going to use the zero density approach. When the conductor is smaller than x to the eta for some small parameter eta. So whereas in the primes result, the zero density methods work on the entire range, you can prove the result just using zero density. That isn't the case here. And that's because the relationship between the character sum over smooth numbers and ls chi is much more indirect. There's this kind of exponentiation that goes into it. So ls chi x chi n, this somehow corresponds to ls chi y, and this looks like an exponential of so there's some relationship between character sums over primes, ls chi and ls chi y, but it all goes in this exponential. So can't go further than this, but fortunately once I get past there, so 3, then use the large sieve directly. If the conductor is bigger than that. And that's okay because although I'm still losing out because of the density, the Q is so big in the denominator that I'm going to win anyway. And just say about this part, because everything is going on in the exponent, I have to be very careful about how I band the size of sum of chi of p over p to the s. And I'm going to use the explicit formula, but I can't just band things in the kind of usual way. I need to use log free zero density. Because if I lose a log factor in the exponent, that's kind of a disaster. Right, so I'll finish just by making 2 remarks about this theorem. So in the Bombieri Vinogradov theorem for primes, the result is ineffective unless a is really small. So a is a half or 1 or something. Now that is still the case here, but here we have this other factor there that's decaying. So if y is like square root log x, say, I can choose a is a half or a is 1, so I have an effective result. I can still have a pretty good bound because the e to the minus u over log squared u is going to 0 very fast. So what I'm saying there is the Bombieri Vinogradov theorem here, provided y isn't too big, can be both a good bound and effective. That is not the case in the primes, and that's because the C equals 0 plays a different role. It's a manifestation of the same thing. And the other thing is that, as I said, y smooth numbers are much sparser than primes when y is small. So this is a decent band that's holding for a very sparse set. There aren't too many examples of this kind of theorem that work for very sparse sets. Okay, so that's what I want to say. So I guess Linux theorem is not too hard because the result of sound that I kind of mentioned that allows q to be up to y, this only requires that log x over log q tends to infinity. So you can just directly extract something from that, I think.
So what would be the limitation in terms of the power of q? What would you take?
So I don't know exactly what constant you get as a power of q, but there'd be some bigger of one there.
Are we talking about Linux for almost prime?
For smooth numbers, I guess.
I mean not almost.
No, for small numbers.
Sorry, I meant.
Yeah, so the result of sound, basically, this is like 5.5 for Linux. XY if
Yes, I'm perplexed about one point. You're explaining that for small y, you can't use a large sieve because the large sieve, or at least the Berlin inequality, which estimates the norm with the worst case of a, you're overcoming that. You didn't say. You said you're using zero density methods.
yes.
It wasn't clear to me how you overcame that.
Okay.
You're not using a large sieve inequality.
No. So I said that ls chi, so I can express the character sum I'm interested in as a contour integral of ls chi y. And ls chi y roughly looks like an exponential with a sum over primes. And the sum over primes I know is related to zeros of ls chi by the explicit formula. So if I know that for my particular L function I don't have many zeros close to 1.
So then are you using just the standard zero density estimates of Bombieri?
Has to be log free.
Log free version.
Yes.
That's what you. But that's the input.
Yes.
It's a bit like the proof of Linux theorem. If you have a zero, it's easier.
Right.
Yeah. Yeah.
Now the fact that the thing moves, gets smaller.
It helps for a different reason.